a slow, poetic meditation on infinity. The viewer is invited into a vision of drifting through endless space. No walls, no boundaries, no horizon that marks an end. Yet in human experience, everything has a limit. A room ends at its walls. A road fades into the horizon. Even a lifetime ends with death. But space itself, if there is no edge, no ending, then what does infinity mean? Is infinity a physical reality, or a concept born of mathematics? If one could travel forever, would one eventually return to where they began, like circling the surface of a sphere? Or does the universe stretch endlessly outward, expanding into nothing, a void without borders? This opening establishes the tension. The human mind seeks limits, but the cosmos whispers a truth without them. The question is not just where space ends, but whether end is even a meaningful word when speaking of infinity. Welcome. You are watching Whisper Science. Make sure to subscribe and join us for more amazing science content. Now, let's move back to the video. Night after night, long before cities lit the skies, human beings tilted their heads upward and saw a mystery so vast it seemed beyond comprehension. Above them stretched a canvas of cold fire. Stars scattered like grains of luminous sand across an endless ocean of black. The horizon of the earth gave the illusion of an edge, a dome perhaps, or a ceiling. Yet the sky itself whispered otherwise. It did not end, it only deepened. For the first civilizations, the question of boundaries was not abstract philosophy. It was survival. The heavens dictated the rhythm of planting and harvest, of flood and drought, of the return of seasons. To understand the sky was to understand life itself. And so, temples rose, aligned with solstices and equinoxes, each stone marking the passage of time beneath what appeared to be a limitless vault. Ancient Indian texts described countless worlds, woven into cycles of creation and destruction. Chinese chronicles imagined heavens that repeated in patterns, reflecting the order of earthly rule. In Greece, the philosopher Anaximander spoke of the boundless, the apeiron, an infinite source beyond all things. Yet his student Aristotle recoiled from the abyss. For him, the heavens were a finite sphere of crystalline perfection, enclosing Earth at its heart. Beyond the outermost stars, he said, lay nothing at all. No space, no time, no outside. But not all agreed. A voice, faint yet unsettling, rose against this picture of a neatly bounded cosmos. Archytas, a contemporary of Plato, posed a paradox as sharp as an arrow. Imagine reaching the supposed edge of the heavens. Could one not stretch out a hand, or hurl a spear, beyond that boundary? If so, what lies there? If not, what could possibly block the path, if nothing is beyond? His thought tore open a wound that would never quite heal. Either space must be infinite, or something stranger still must lie beyond its veil. The centuries turned. Astronomy, in its infancy, was bound by the naked eye. Even the most careful observations by Hipparchus mapping the stars, or Ptolemy constructing his geocentric spheres, could not break the illusion of a finite firmament. To gaze upward was to see order, not infinity. The sky was a clockwork, precise, symmetrical, contained. And yet, in silence, doubt gathered. With the rise of Islamic scholarship in the medieval world, inherited Greek models were tested against sharper mathematics and careful measurements. Al-Hasan, the great Arab physicist, rejected Aristotle's solid celestial spheres, insisting the heavens were not crystalline shells but empty space through which light travels freely. Al-Biruni and others debated whether the universe had a boundary at all, or whether space extended endlessly, filled with stars we could not see. For them, infinity was not heresy. It was a horizon of questions. Still, it was the Renaissance that shattered the walls of the old cosmos. Copernicus displaced Earth from the center, declaring the sun the anchor of celestial motions. But even in his model, the stars remained fixed at the edge, forming a distant shell. It was Giordano Bruno, fiery and unyielding, who dared to break the dome entirely. He proclaimed that the universe was infinite, filled with uncountable suns, each surrounded by their own worlds. For this vision, he was condemned. Infinity, it seemed, was not only a challenge to science, but to power, to belief, to the human craving for limits. Then came Galileo, with a small tube of glass and lenses polished by hand. Through this instrument, the sky revealed its hidden multiplicity. The Milky Way, once a pale smear across the heavens, dissolved into a river of innumerable stars. Moons circled Jupiter. Mountains and craters scarred the face of the moon. The cosmos was no longer perfect, no longer finite, no longer knowable by simple reason alone. Each observation hinted at depth without end. The stars were not scattered jewels on a dark dome. They were distant suns, burning in a space whose boundaries retreated faster than thought could follow. The 17th century brought Kepler, charting the planetary orbits as ellipses, not circles, and Newton, unveiling the law of universal gravitation. His equations suggested no natural limit. Matter, once set in motion, would travel endlessly through space unless acted upon. The universe, in Newton's vision, stretched without boundary, a stage of infinite extent upon which every star and planet performed its eternal dance. Yet this infinite cosmos carried within it a paradox. If stars filled an endless expanse, then every line of sight should terminate in a star, and the night sky should blaze like the surface of the sun. This was Olber's paradox, though it would not be fully articulated until centuries later. Infinity, once embraced, threatened to undo the very darkness of night. Each breakthrough revealed not a cage of stars, but an expanding corridor of mystery. The invention of more powerful telescopes in the 18th and 19th centuries, by Herschel and others, multiplied the known boundaries. Herschel mapped the Milky Way, counting thousands of stars, but even his vast survey ended not in walls, but in incompleteness. Beyond his charts, faint smudges of light beckoned. Some thought them mere clouds of gas. Others suspected whole galaxies, island universes, scattered in an infinite sea. The journey from Temple skywatchers to Herschel's sweeping catalogues reveals a truth both simple and profound. The more humanity looked outward, the less it found an edge. Each horizon dissolved into another. Each boundary gave way to a deeper field. Infinity, once a philosophical provocation, had begun to emerge as a scientific reality. But it remained an uneasy one. For to confront infinity is to confront a concept the human mind was never designed to hold. Here, at the dawn of modern astronomy, the stage was set. The ancient paradox of Archytas had grown into a scientific wound. Infinity was no longer a speculation, no longer confined to metaphysics. It pressed upon the data itself, upon the sky, as recorded in glass plates and telescopic lenses. Was space truly without limit? Or was its vastness only a temporary illusion, to be overturned by some future revelation? The answer lay hidden in the starlight, waiting to be uncovered. For now, humanity had taken its first true glimpses of the infinite, and what it found was not closure, but a door. One that opened into a corridor without end. Infinity, a word that seems simple, yet it carries a weight that has unsettled philosophers, mathematicians, and scientists for centuries. For in mathematics, infinity can be manipulated, compared, and classified. But in the physical universe, infinity does not behave so neatly. It destabilizes laws, tears apart expectations, and threatens to unravel the very structures of physics. When Isaac Newton unveiled his Principia in 1687, he built the universe upon the bedrock of universal gravitation. Every mass attracted every other mass, no matter the distance. Planets circled the sun not by chance, but by the invisible pull of this law. But Newton's mathematics carried an unsettling implication. If the universe were infinite, and filled with infinite stars, then every star would be pulled by the gravity of countless others in every direction. The entire cosmos should collapse under the weight of its own infinite attraction. And yet, it had not. Something about infinity defied his own equations. Newton himself admitted unease, suggesting that only the hand of God could maintain balance in an endless universe. For the first time, infinity had entered physics as a paradox, not a solution. The centuries that followed only deepened this tension. By the early 19th century, astronomers faced a darker puzzle. If space truly stretched forever, and if stars filled that endless canvas, then every line of sight should eventually strike the surface of a star. The sky, in all directions, should blaze with the brightness of the sun. Night should not exist. Darkness should be impossible. This became known as Olber's paradox, named after Heinrich Wilhelm Olbers, though others before him, Kepler, Halley, Even Descartes had felt its shadow. The paradox was simple, brutal, and devastating. An infinite, static, eternal universe would shine with unbearable light. And yet, each night, the heavens remained silent and dark. The paradox was more than a riddle of brightness. It was a philosophical wound. If the universe could not be both infinite and static, then something fundamental in human understanding was wrong. Either space had an edge, a boundary that cut off the light of distant stars, or the universe had not always existed. Perhaps it had a beginning. Perhaps it was in motion. Each possibility was as radical as it was terrifying. The shock of infinity rippled far beyond astronomy. In mathematics, Georg Cantor, working in the late 19th century, revealed that infinity was not a single concept, but a hierarchy. There were infinities, larger than infinities, countable and uncountable, each more bewildering than the last. His discovery broke the boundaries of logic itself, but it also broke him. Tormented by critics, plagued by doubt, Cantor spent his later years in and out of asylums, haunted by the enormity of what he had uncovered. Infinity was not just a mathematical curiosity, it was a force that consumed minds, leaving even the most brilliant shaken. In physics, the arrival of thermodynamics and the concept of entropy added another blow. If the universe were eternal, without beginning, then over infinite time every star would have burned its fuel. Every gradient of energy would have dissipated, every system would have decayed into uniformity. An infinite past would have already delivered the universe into heat death. Yet here we are, surrounded by shining stars and galaxies, alive with structure. Infinity, again, threatened contradiction. If time itself had stretched forever, we should not exist. The fact that life looks out upon the cosmos seemed to demand that time had a beginning. Even Albert Einstein, when he introduced his general theory of relativity in 1915, was shaken by the specter of infinity. His equations described a dynamic fabric of space-time, bending under the weight of mass and energy. But when applied to the cosmos as a whole, they predicted motion. Either the universe must be expanding or contracting. Einstein resisted. He believed, like most of his contemporaries, in a static eternal cosmos. To suppress the motion in his equations, he introduced a cosmological constant, a repulsive force to hold infinity in balance. Later, he would call it his greatest blunder. Yet behind his hesitation was not just a mistake in physics. It was a refusal to embrace the infinite consequences of his own mathematics. For infinity always carried with it something unstable, something that undermined certainty. A finite universe might be describable, chartable, predictable, but an infinite one defied closure. How can one define the density of matter if matter is endless? How can one assign probabilities if every outcome, given infinite space and time, must eventually occur? In an infinite cosmos, even the laws of chance collapse into paradox. The shock of infinity reached into the human spirit as well. For to contemplate an endless universe was to confront one's own minuteness. If stars stretch without end, if galaxies multiply beyond all measure, then the Earth is not merely small, it is negligible. An invisible point, adrift in boundless night. Copernicus had displaced humanity from the center. Infinity threatened to erase the center altogether. There would be no preferred place, no privileged position, no cosmic boundary to frame the story of life. Infinity was not just large, it was annihilating. And yet, paradoxically, the night sky offered both terror and comfort. The very darkness that haunted Olber's paradox preserved the possibility of meaning. For if the universe were infinite and static, filled with stars from eternity, then night could not exist. Darkness itself was evidence that the cosmos was stranger than infinity allowed. Perhaps it had a beginning. Perhaps it was finite, or curved back on itself, or expanding into realms unknown. Infinity was not the end of questioning, it was the beginning. Thus, by the dawn of the 20th century, infinity had become the silent antagonist of cosmology. It haunted Newton's gravity, blazed in Olber's paradox, unsettled thermodynamics, destabilized relativity, and consumed the greatest mathematicians. It was no longer a speculative horizon, as it had been for Archytas or Bruno. It was a scientific shockwave, demanding explanation. Infinity had revealed itself as more than a concept. It was a mirror held up to physics, reflecting contradictions and impossibilities. It forced scientists to choose. Either the universe was not infinite in the ways they imagined, or their understanding of light, gravity, and time was incomplete. Both options promised revolutions. The question was no longer whether infinity existed. The question was how deeply it would change everything humanity thought it knew. For millennia, the universe was imagined as eternal, unchanging, a vast stage upon which the stars burned in fixed positions. The sky seemed permanent, the galaxies silent and unmoving, a cathedral of light without history. But in the 20th century, this illusion shattered. The cosmos was revealed not as a static backdrop, but as something alive, stretching, shifting, growing. Space itself was expanding. It began with mathematics. In 1915, Albert Einstein presented his general theory of relativity, a radical vision of gravity not as a force, but as the bending of space-time. Mass and energy shaped the fabric of the cosmos. The fabric, in turn, guided the movement of planets and light. When applied to the universe as a whole, Einstein's equations did not allow for stasis. Space could not simply sit still. It must curve, evolve, expand, or contract. Yet this outcome conflicted with Einstein's belief in a steady cosmos. To preserve stability, he introduced a new term, the cosmological constant, a repulsive force to counteract gravity and freeze the universe in place. It was a delicate balancing act, like resting a pencil on its tip, beautiful in its symmetry, but unstable at the slightest touch. Meanwhile, others embraced the mathematics without hesitation. The Russian physicist Alexander Friedmann, in 1922, solved Einstein's equations in a way that described an expanding cosmos. His solutions suggested that galaxies were not fixed in space, but carried outward by the stretching of space-time itself. Across Europe, Georges Lemaître, a Belgian priest and physicist, reached the same conclusion. He proposed that the universe began from what he called a primeval atom, an initial burst that expanded into the cosmos we see today. His vision was radical, a universe with a beginning, expanding from an origin point. The theory remained speculative until data intervened. In the 1920s, astronomers debated the nature of faint, cloud-like smudges seen through telescopes. Were they nebulae, gas clouds within our own Milky Way, or island universes, galaxies in their own right, beyond our stars? The debate ended with the work of Edwin Hubble at Mount Wilson Observatory in California. Using the powerful 100-inch Hooker telescope, he measured the distances to several of these nebulae, employing the pulsations of Cepheid variable stars as cosmic yardsticks. The results were staggering. These smudges were not clouds nearby. They were entire galaxies, millions of light-years away. The Milky Way was not the universe, but a single galaxy adrift in a sea of galaxies. Then came the revelation that would transform cosmology forever. Hubble measured the light from distant galaxies and found it stretched, shifted toward the red end of the spectrum. This redshift was the fingerprint of motion. The galaxies were receding, and not just some, but all, in every direction. The farther a galaxy lay from us, the faster it moved away. The universe was not static. It was expanding. What Hubble uncovered was more than motion. It was evidence that space itself was stretching. The galaxies were not flying apart through a pre-existing void, like fragments from an explosion. Rather, the fabric of space between them was growing, carrying galaxies outward as raisins drift apart in rising dough. This subtle distinction marked the birth of modern cosmology. The universe had no fixed edge to expand into. It expanded within itself, without boundary. Infinity, once abstract, had taken on dynamic form. The shock reverberated through science. Einstein himself visited Hubble in 1931 and reportedly admitted that resisting expansion had been his greatest blunder. The cosmological constant, invented to freeze the universe, had concealed its true motion. Now, the cosmos appeared restless, a story with direction and change. Yet the implications were even more profound. If the universe is expanding today, then in the past it must have been smaller, denser, hotter. Extrapolate backward, and all of space, all matter, all energy, converged to a single beginning. The universe had a birth. Lemaître's primeval atom became the seed of what would later be known as the Big Bang. This idea was radical in more than science. It unsettled philosophy. For centuries, infinity had implied timelessness, a universe eternal and unchanging. But now the evidence suggested that infinity itself had an origin, that time had a first moment. The cosmos was not boundless in age. It was 13 to 14 billion years old, finite in history if not in extent. For the first time, infinity was married to creation, an endless universe born from a single beginning. But expansion carried other mysteries. If galaxies are receding, then what lies beyond them? Does expansion continue without limit, driving galaxies apart into an infinite void? Or does the universe curve back upon itself, finite yet unbounded, like the surface of a sphere? Measurements alone could not yet answer. Infinity lingered as a possibility, but now it was an infinity in motion, accelerating outward, changing with time. The expanding universe also redefined human perspective. No longer was Earth the center of creation, or even the Milky Way. Every observer, in every galaxy, would see others receding. Expansion had no privileged point. New central origin. The cosmos looked the same from every vantage. Infinity was not out there beyond reach. It was everywhere, stitched into the very structure of space. For astronomers of the early 20th century, this vision was as unsettling as it was exhilarating. The night sky, once thought eternal, now told a story of unfolding. Infinity had become history, and history demanded a future. Would expansion continue forever, thinning galaxies into cold isolation? Or would gravity one day halt the outward rush, pulling everything back in a cosmic collapse, a big crunch? The answers lay hidden in the faint glow of distant starlight, waiting for new generations of instruments to uncover. By the mid-20th century, technology rose to the challenge. Radio astronomy, photographic plates, and, eventually, satellites above Earth's atmosphere allowed astronomers to probe deeper. In 1965, Arno Penzias and Robert Wilson, working at Bell Labs, discovered a faint microwave signal coming from every direction of the sky, relic radiation from the early fireball, proof of a hot, dense beginning. The expanding universe had left its fingerprint across the heavens. What Hubble saw in galaxies, the cosmic microwave background, confirmed in the very fabric of radiation itself. The discovery ended centuries of debate. The universe was not static. It was not eternal in its present form. It was expanding, cooling, evolving. The cosmos had a birth, and it was still unfolding. Yet this victory did not erase the unease. For expansion only deepened the question of infinity. If the universe began in a finite state, how could it now be infinite in extent? If galaxies are rushing outward, what lies beyond the horizon we cannot yet see? Expansion revealed history, but it did not resolve the paradox. Infinity remained, but it was now dynamic, elusive, woven into the very breath of space itself. In this transformation, science took a decisive step. The universe was no longer a static canvas for human wonder. It was a living narrative, a story of beginning and becoming. Infinity was no longer passive. It was kinetic, stretching, redshifting, expanding. And within that story, humanity found itself not at the center, but carried along, adrift on a fabric that grew beneath its feet. The expanding universe was not just a discovery. It was a revelation that space itself is restless, that time itself has direction, and that infinity, far from being still, is forever in motion. The revelation of expansion brought with it a profound shift in perspective. The universe was no longer static, no longer eternal in its present form. It was unfolding, stretching, evolving. But expansion, when traced backward, carried with it an inescapable truth. The cosmos had a beginning. If it had a beginning, then it also had limits, not of space, but of time. And from this limit emerged one of the strangest consequences of cosmology: the cosmic horizon. At first glance, the night sky seems endless. No matter where one looks, stars and galaxies glimmer in all directions. Yet what we see is not the universe as it is, but the universe as it was. Light takes time to travel, and the farther it comes from, the older it is when it arrives. To gaze into the sky is to look backward through history. A star 100 light-years away is seen as it was a century ago. A galaxy 1 billion light-years away shines as it was a billion years in the past. The telescope does not only magnify, it resurrects. Each photon is a messenger, bearing the memory of ancient times. Follow this logic to its limit, and the universe reveals a strange boundary. If the cosmos is 13.8 billion years old, then no light can have traveled farther than 13.8 billion light years to reach us. Beyond that, the past is inaccessible. Beyond that, the universe exists, but it cannot be seen. This invisible sphere, centered on every observer, is called the observable universe. It is not the edge of reality, but the edge of visibility, in every direction. This horizon wraps around us at a staggering distance of 46 billion light years, larger than the age of the cosmos suggests, because space itself has been expanding while the light traveled. What lies beyond it remains hidden, veiled not by walls, but by time itself. The universe may continue indefinitely, but we are forever confined to our bubble of light. This horizon is not smooth. It has texture, memory, scars. In 1965, Arno, Penzias, and Robert Wilson accidentally stumbled upon a faint hiss in their radio antenna. Noise that came from no earthly source and no single star. It came from everywhere, all at once. They had found the cosmic microwave background, the faint afterglow of the Big Bang, stretched into microwaves by the expansion of space. Here, at the edge of our observable universe, lies the most ancient light possible. A photograph of the cosmos when it was only 380,000 years old, a child just learning to walk. In that glow, satellites like COBE, WMAP, and Planck have mapped subtle ripples, slight temperature differences, tiny variations in density. These ripples are the seeds of everything. From them, galaxies would form, stars would ignite, planets would condense. The cosmic horizon does not simply mark an edge, it marks the origin of structure itself. And yet, it deepens the mystery. For if the observable universe is bounded, what of the unobservable? What lies beyond the curtain? If infinity stretches outward, then the vast majority of the cosmos remains forever beyond our reach. There may be galaxies, clusters, and vast structures larger than anything we know, but their light will never arrive. They exist outside the horizon of causality. They are, to us, as if they were not there. This realization transforms the meaning of infinity. The universe may be endless, but infinity itself is fractured by time. To every observer, the cosmos appears finite, bounded by a personal horizon. Each being inhabits their own cosmic bubble, overlapping with others, but never encompassing all. Infinity exists in theory, but never in experience. The cosmos is at once infinite and confined. The paradox deepens further with the discovery that expansion is not slowing, as once imagined, but accelerating. In 1998, two independent teams studying distant supernova found that galaxies are receding faster and faster, something unseen. Dark energy is pushing space apart. With acceleration, the horizon is not fixed. It grows narrower in influence. Galaxies once within reach are now carried away faster than light can bridge the gap. In the distant future, most galaxies will slip beyond the horizon, vanishing from view. The night sky will grow emptier, leaving only the faint island of the local group, while the wider universe drifts irretrievably away. The horizon is not just a limit of observation. It is a limit of knowledge. Physics depends on data, on light and particles that arrive to tell their story. But beyond the horizon, no information can cross. There may be regions where the laws of physics are the same, or regions where they are different. Entire realms of space-time may exist beyond our grasp, governed by other conditions, other constants, yet they remain forever invisible. For science, this is both a frustration and a revelation. Reality may be larger than evidence allows. Philosophically, the horizon is a reminder of human finitude. Just as the ocean horizon once confined sailors until they learned to cross it, the cosmic horizon confines thought itself. But unlike the seas, it cannot be crossed. No ship, no telescope, no future technology can pierce it. It is not a boundary of distance, but of time. And time cannot be reversed. The cosmic horizon also raises a haunting question. If each observer has their own horizon, does the universe look different from elsewhere? For a galaxy on the far edge of our visibility, the cosmos centers on it as well, with its own bubble of light. Each perspective is both complete and incomplete. Each is a fragment of infinity, framed by the speed of light. Infinity, therefore, is not universal experience, but fragmented truth. This realization unsettles the notion of a single, shared cosmos. The universe we describe, the one mapped by telescopes and satellites, is only a slice, a projection within our horizon. It may not be the universe, but merely our version of it. The greater whole, beyond our reach, may differ in ways we cannot imagine. Infinity hides itself behind a veil of causality, permitting only glimpses, never totality. And so, the mystery deepens. The cosmic horizon is both gift and curse. It gives us the earliest image of the universe, yet denies us access to its fullness. It confirms expansion, yet conceals infinity. It reveals our origin, yet withholds our destiny. In the silence of the night sky, the horizon hangs as a paradox. We live in a universe without edges, yet bound by a limit. We inhabit infinity, yet only within a bubble. To look upward is to see eternity, and yet to know it is not complete. The cosmic horizon does not merely mark where sight ends, it marks where mystery begins. Infinity, when spoken in human language, seems absolute. A straight line stretching forever, a space without end. Yet in the mathematics of the cosmos, infinity is not so simple. It wears shapes, it bends, it folds. The geometry of the universe, the way space itself is curved, determines whether infinity is real or whether it is an illusion. Einstein's general relativity does more than describe gravity. It offers a language for space itself. According to relativity, the distribution of matter and energy dictates how space bends. A planet curves space-time locally, guiding the path of moons. A star bends it more strongly, deflecting even the trajectory of light. But what of the cosmos as a whole? If all galaxies, stars, and radiation together create the curvature of the universe, what is the global shape of everything? Three possibilities arise, each as strange as it is profound. In this geometry, space is finite, but unbounded. Imagine living on the surface of a sphere. Walk forward forever, and you will eventually return to where you began. No walls, no edges, yet a natural limit. The surface curves back on itself. Applied to the universe, this means space contains a finite volume, but without borders. Galaxies curve around in cosmic arcs, and if one could travel far enough, one might circle the universe endlessly. Infinity here is an illusion, born of the inability to perceive curvature across such vast scales. In such a cosmos, the night sky would be like a hall of mirrors. Light, circling through space, might one day return from behind, creating multiple images of the same galaxy at different ages. The universe would be self-contained, a cosmic loop. It would not stretch into infinity, but into continuity. For philosophers, this closed model resonates with cycles, a universe that is whole, finite, yet eternal in its return. Here space curves outward like a saddle, negative in its geometry. In this model, space expands forever, thinning and stretching without bound. Galaxies grow more and more isolated as the fabric of space rushes outward. The saddle shape offers no return, no closure, only an endless expanse. In such a universe, infinity is real. It is not a trick of curvature, but a literal, boundless ocean. Space does not fold back. It unrolls endlessly, each step into the future, leading farther from all others. This geometry offers no comfort of return. Instead, it describes a cosmos doomed to separation. Every galaxy drifts farther into solitude. Every cluster eventually dissolves into the dark. An open universe is infinite, not only in extent, but in loneliness. Its shape is expansion itself. Neither curving inward like a sphere, nor outward like a saddle, it is the delicate balance point between the two. Here, space resembles an infinite plane, like a sheet of paper extending without end. Galaxies drift upon it, their motions governed not by the folding of space, but by its uniform flatness. In such a cosmos, infinity appears as literal extension, uncurved, undistorted. It is the simplest geometry, yet perhaps the most unsettling. For if the universe is perfectly flat, then its infinity may be real, not apparent. It stretches without border in all directions, with no curvature to rein it back. But flatness is also precarious. A slight excess of matter would curve it inward. A slight deficit would curve it outward. The balance is so fine that cosmologists call it critical density. The question of whether the universe is flat, open, or closed is not just about shape. It is about destiny. How does one measure the geometry of the cosmos? The universe is far too large to walk across, too vast to survey by ordinary means. Instead, scientists turn to light itself, the most ancient light of all, the cosmic microwave background. Those ripples, mapped by Kobe, WMAP, and Planck, do more than show the seeds of galaxies. They encode geometry. By measuring the angular size of the ripples, how large or small they appear across the sky, physicists test whether space bends them inward, outward, or not at all. The results are remarkable. The ripples appear consistent with flatness. The universe, on the largest scales we can measure, seems balanced at critical density, not closed, not open, but flat. If true, then infinity may not be an illusion of curvature. It may be real, stretching endlessly in all directions. Yet uncertainties remain. Our horizon limits us. We can measure only within the bubble of the observable universe. Beyond that, the geometry may shift, unseen. The cosmos may curve in ways we cannot detect, hiding its true nature beyond the reach of light. Philosophically, each geometry reshapes the meaning of infinity. A closed universe denies it. Infinity is not real, but apparent, looping endlessly. An open universe embraces it. Infinity is vast, unstoppable, ever expanding. A flat universe balances on the knife's edge. Infinity as literal extension, but fragile, dependent on exact balances of matter and energy. Each possibility carries implications for the fate of everything. In a closed universe, expansion may one day halt, reversing into collapse, a big crunch. In an open or flat universe, expansion may continue forever, driven onward by dark energy, until galaxies disappear beyond one another's horizons. Geometry is not abstract. It is destiny written in shape. And yet, deeper still, geometry connects with something even stranger. Quantum cosmology suggests that the entire universe may be a fluctuation of a vacuum, emerging spontaneously from nothing. In such models, closed universes may bubble forth, finite yet complete. Open universes may stretch endlessly, spawned from eternal inflation, each bubble one cosmos among many. Flat universes may extend like infinite fields, born from the balance of quantum chance. Infinity, therefore, is not only a question of geometry, but of origin. Einstein himself suspected that geometry held the key to understanding the cosmos. But he could not have foreseen the precision with which satellites would later map the microwave background, tracing the faintest ripples of light to reveal the shape of everything. The data points toward flatness. But flatness itself raises further questions. Why should the universe balance so perfectly at critical density? Why does infinity, if it exists, rest upon such delicate precision? This puzzle is known as the flatness problem, and it haunts cosmology still. Inflation theory offers one answer. In the first fraction of a second after the Big Bang, space may have expanded at an exponential rate, stretching any initial curvature into near-perfect flatness, like a balloon inflated until its surface appears smooth. If so, then infinity may be not a fundamental truth, but a byproduct of cosmic inflation. The universe may appear flat and infinite, because inflation stretched it so vast that curvature is imperceptible within our horizon. Beyond, the geometry may curve in ways forever hidden. The geometries of the infinite reveal a profound truth. Infinity is not simply about size. It is about shape, curvature, balance. It is not enough to ask whether space goes on forever. One must ask how it bends, how it connects, how it defines motion and fate. Infinity may be curved into loops, stretched into saddles, or balanced upon planes. Each vision transforms not only cosmology, but philosophy itself. Infinity can mean eternal return, eternal expansion, or eternal flatness. It can be an illusion, or it can be real. For humanity, the question remains unresolved. Telescopes probe, satellites measure, equations predict, but the horizon limits certainty. Beyond the edge of sight, the geometry of the infinite remains veiled. Perhaps infinity ends in curvature. Perhaps it does not end at all. And so the cosmos deepens its riddle. Space has no edge, yet geometry may shape its meaning. Infinity wears disguises, and through them, the universe whispers both promise and enigma. Infinity, when imagined as endless distance, is already unsettling. But when it enters physics, it does not merely stretch horizons. It begins to break the very machinery of science. For infinity, when applied to equations, often refuses to behave. It produces contradictions, paradoxes, and infinities stacked upon infinities. It is here, in the delicate framework of quantum theory and cosmology, that infinity becomes not just a mystery of scale, but a threat to understanding itself. In the realm of quantum mechanics, the vacuum is never empty. Even in the deepest void, particles and antiparticles flicker in and out of existence, borrowing energy from nothingness and returning it in fleeting instants. This restless quantum sea fills all of space. But when physicists calculate the total energy of this vacuum, the numbers spiral into catastrophe. According to quantum field theory, the energy density of empty space should be infinite. Yet when compared to the observed universe, the vacuum energy is not infinite at all. It is extraordinarily small. So small that the discrepancy between theory and observation is greater than any mismatch in the history of science. Known as the cosmological constant problem, it is the most severe clash between infinity and reality. The equations insist upon infinity, but the universe refuses to show it. This is not the only wound infinity carves into physics. At the heart of black holes, Einstein's equations predict a singularity, a point of infinite density, where space-time curvature becomes infinite, and the known laws of physics break down. Infinity here is not vastness, but compression. It is not distance without end, but matter without limit. Within singularities, the smooth fabric of relativity tears into impossibility. Physicists suspect that quantum gravity, a theory uniting the quantum with relativity, would soften these infinities, replacing them with something finite and comprehensible. But until such a theory is found, singularities remain scars in the mathematical description of reality. Even in the expanding universe itself, infinity complicates the story. The theory of cosmic inflation suggests that in the first instant after the Big Bang, space expanded faster than light, stretching quantum fluctuations into the seeds of galaxies. But inflation may not have ended everywhere at once. Instead, it may continue eternally in pockets of the cosmos beyond our horizon. Regions of space would stop inflating, cool, and form bubble universes, like ours. Others would continue inflating, endlessly. This vision of eternal inflation produces not one universe, but an infinite multiverse. Infinity does not stop at space. It multiplies in kind. Here, a new problem arises. The measure problem. In an infinite multiverse, every possible event not only happens, but happens infinitely many times. Somewhere, there is another Earth. Somewhere, there are infinite Earths. Some nearly identical, some wildly different. In such a cosmos, how can probability retain meaning? If everything occurs infinitely often, how can science predict anything? The concept of likelihood dissolves. Infinity, once imagined as possibility, becomes paralysis. This collapse of probability exposes the fragility of human understanding. Science depends on comparison. This event is more likely than that, this outcome more probable than another. But in an infinite ensemble, such comparisons fail. The laws of physics may still operate locally, but globally, infinity erases distinctions. The multiverse becomes not an explanation, but a fog. Some physicists embrace this vision. For them, infinity is the natural consequence of cosmic inflation in quantum mechanics. Others recoil, seeing in it the end of predictive science. Still others propose ways to tame infinity, to cut it down into manageable measures, weighting probabilities, defining cutoffs, reshaping the mathematics to restore meaning. Yet no consensus exists. Infinity remains a paradox wrapped in equations. Beyond cosmology, infinity complicates even the foundation of mathematics within physics. Georg Cantor revealed that infinities come in hierarchies, some countable, like the set of integers, others uncountable, like the continuum of real numbers. In modern physics, both kinds appear. Quantum states form Hilbert spaces of uncountable dimensions. String theory suggests landscapes of possible universes so vast they verge on the infinite. Mathematics tolerates these infinities, but when they intersect with physical predictions, the results are unsettling. Physicists often employ a technique called renormalization, cutting away the infinities that erupt in calculations of quantum fields. With careful procedure, infinities cancel, leaving finite predictions that match experiments with astonishing accuracy. The magnetic moment of the electron, calculated this way, agrees with observation to more than 10 decimal places. It is one of the most precise agreements between theory and nature ever achieved. And yet, this success carries an unease. Renormalization works, but it is, in essence, a way of ignoring infinities rather than resolving them. Infinity remains, lurking beneath the mathematics, patched but not healed. The confrontation with infinity reaches perhaps its most unsettling in cosmology's ultimate questions: the beginning and the end. If the universe began in a Big Bang, what came before? If it ends in heat death, with all energy dissipated, what lies beyond? These questions teeter at the edge of infinity. Time itself may be finite in age, but infinite in possibility. Some theories imagine cycles of universes, each collapse birthing a new expansion, an eternal return. Others imagine a false vacuum, a metastable state of space-time itself, that could decay at any moment, rewriting the laws of physics in a bubble, expanding at nearly the speed of light. Here, infinity takes the form of eternal risk. Not the comfort of boundless space, but the abyss of boundless fragility. Infinity complicates not only equations, but meaning. For if everything exists in infinite copies, what does individuality mean? If every outcome occurs, what is the significance of choice? Philosophers and physicists alike wrestle with this. Some argue that infinity robs life of uniqueness. Others argue that uniqueness lies precisely in the local, in the finite perspective of beings who can only experience one thread among countless. Infinity, in this view, does not erase meaning. It magnifies it by showing how rare consciousness is amid the ocean of possibility. Infinity complicates physics because it challenges the boundary between the calculable and the unknowable. It appears in singularities, in quantum fields, in cosmic expansion, in probability itself. Sometimes it is cut away by mathematics. Sometimes it is embraced as truth. Sometimes it is feared as the dissolution of science. Yet the very fact that infinity emerges again and again suggests it is not an error. It may be a clue, a signal that our theories, powerful as they are, remain incomplete. Each appearance of infinity may be pointing toward a deeper layer of reality, one in which these contradictions resolve into coherence. Perhaps infinity is not an obstacle, but a doorway. Until that deeper framework is found, infinity remains both the most dangerous and the most essential idea in physics. It complicates, destabilizes, unsettles, but it also illuminates the path forward. For every paradox, every singularity, every breakdown is an invitation to seek the laws that lie beyond. The mystery of infinity does not rest in philosophy alone. It is pursued, piece by piece, by the instruments of science: mirrors of glass, detectors of light, machines that smash particles into fragments of energy. For infinity may be unreachable in totality, but it leaves traces. It bends the light of galaxies. It echoes in radiation older than stars. It hides in the mathematics of quantum fields. And so humanity builds tools to follow these threads, stretching technology to its limits, to glimpse what lies beyond the horizon of knowledge. The story begins with telescopes, the oldest companions in our search. From Galileo's first lens to the great observatories of the 20th century, telescopes have always been humanity's windows into distance. But in the modern era, they no longer merely magnify. They probe the geometry of the cosmos itself. The Sloan Digital Sky Survey, for example, has mapped millions of galaxies across the sky, tracing the large-scale structure of the universe. These galaxies are not scattered at random. They form filaments and voids, a cosmic web stretching across billions of light-years. In their patterns lie clues to expansion, curvature, and the distribution of dark matter. The survey's vast maps serve as tests of infinity. Are we seeing the whole of the cosmos, or only a fragment shaped by horizons we cannot cross? Above Earth's atmosphere, satellites have extended this vision further. COBE in the 1990s, WMAP in the 2000s, and most recently the Planck satellite have mapped the cosmic microwave background with increasing precision. This faint afterglow, a remnant of the early universe, carries within it the fingerprint of the cosmos's shape. Tiny ripples in temperature reveal whether space is curved inward, outward, or flat. The data points toward flatness, a universe balanced at critical density. And yet, the very delicacy of this measurement deepens the mystery. For flatness implies infinity, and infinity is not easily embraced. The satellites do not deliver closure, they deliver tension. Beyond telescopes, science turns to accelerators, vast machines that recreate conditions of the early universe in the laboratory. The Large Hadron Collider at CERN, the most powerful ever built, smashes protons together at nearly the speed of light. In these collisions, space is forced to reveal its hidden structure. Out of the chaos emerge particles that speak of fields, symmetries, and forces invisible to daily life. It was here that the Higgs boson was confirmed in 2012, completing the standard model of particle physics. Yet even this triumph leaves unanswered questions. The Higgs field gives particles their mass, but it also hints at the instability of the vacuum itself. If the vacuum is only metastable, a false minimum, then the universe may one day decay into a truer vacuum, rewriting the laws of physics. The collider cannot predict when, but its results remind us that infinity may carry fragility within it. Particle accelerators also probe for evidence of dark matter, the invisible mass that outweighs ordinary matter, 5-to-1. Its presence is seen in galaxies and clusters, curving spacetime, shaping the cosmic web. But its nature remains unknown. Some hope to catch its particles in underground detectors, shielded from cosmic rays. Others hope the LHC or its successors may produce them directly. If discovered, dark matter may transform our understanding of infinity. For it suggests that most of the cosmos lies hidden, unseen, beyond the grasp of light. Even larger projects now set their sights on dark energy, the mysterious force accelerating expansion. The Dark Energy Survey, using telescopes in Chile, scans the southern skies for supernova and the distribution of galaxies, seeking patterns in their expansion. The upcoming Euclid satellite, launched by the European Space Agency, and NASA's Nancy Grace Roman Space Telescope will map cosmic acceleration with unprecedented detail. Each seeks to answer whether dark energy is constant, as Einstein once proposed, or dynamic, evolving over time. The answer may reveal whether the universe expands forever, collapses, or evolves in stranger ways. Infinity itself depends on this hidden force. Yet not all efforts focus on the vast. Some probe the small, where infinity hides in equations. Quantum experiments push boundaries with atom interferometers, precision clocks, and entanglement. The most accurate atomic clocks now measure time so precisely that they would lose less than a second over the age of the universe. These tools allow physicists to test relativity, to measure whether spacetime itself may fluctuate, to search for tiny variations that might signal a deeper theory beneath quantum mechanics. In underground laboratories, detectors filled with liquid xenon wait in silence for faint signals of dark matter. In Antarctica, neutrino observatories buried in the ice listen for ghostly particles from beyond galaxies, traveling unimpeded through matter and time. These experiments turn the Earth itself into a detector, catching whispers of infinity in particles nearly without mass. And then there is the James Webb Space Telescope, humanity's newest and most powerful eye on the cosmos. Launched in 2021, it peers deeper into time than any instrument before, capturing galaxies as they appeared only a few 100 million years after the Big Bang. Some of its findings have already unsettled expectations, revealing galaxies larger and brighter in the early universe than models predicted. Webb stretches the horizon of history, confronting infinity with sharper images, each one a reminder that the cosmos often defies prediction. Future projects aim to go even farther. The Square Kilometre Array, a giant radio telescope under construction in South Africa and Australia, will map hydrogen across cosmic time, tracing the dawn of structure. The Laser Interferometer Space Antenna LISA, planned for the 2030s, will listen for gravitational waves rippling through spacetime, opening a new window on the universe's first instance. Each of these instruments extends the reach of science, not toward an edge, but deeper into infinity's labyrinth. Still, the pursuit is haunted by limits. No telescope, however powerful, can see beyond the cosmic horizon. No accelerator, however vast, can probe energies as high as those of the Big Bang itself. Instruments bring us closer, but infinity always retreats. It remains both target and mirage. The closer we approach, the more it reveals, and the more it conceals. Yet this is the nature of science. It does not demand final answers. It demands sharper questions, more precise measurements, new tools to press against the unknown. Each instrument, a telescope, a satellite, a collider, is a hand reaching into darkness. And though the horizon cannot be crossed, each touch reveals more of what infinity withholds. In the end, the pursuit of infinity through tools is as much philosophical as scientific. For the cosmos is not only observed, it is interpreted. The maps of galaxies, the ripples of microwaves, the tracks of particles, each is a fragment. To weave them into a picture of infinity requires imagination as much as measurement. Instruments provide the canvas. Human thought paints the possibilities. Infinity complicates equations, but tools render its echoes visible. They do not resolve the paradox, they illuminate it. And in doing so, they draw humanity deeper into the mystery, closer to answers, closer to awe, closer to the realization that infinity, though unreachable, leaves fingerprints everywhere. Infinity, a word that lingers like an echo, both alluring and unsettling. Science has pursued it with telescopes and equations, with accelerators and satellites, with theories stretched to the edge of imagination. And yet, after centuries of observation, measurement, and discovery, infinity remains less an answer than a mirror, reflecting back our limits, our hopes, our fragility. Infinity reveals itself not only in mathematics, but in the very fabric of existence. It stands at the beginning, in the singularity where all spacetime converged into heat and density beyond comprehension. It lurks in black holes, where equations collapse into infinities of curvature. It spreads across the geometry of the cosmos, which appears flat, balanced, perhaps endless. It multiplies in the multiverse, where eternal inflation buds infinite realms. In every direction, infinity surfaces, like a tide that cannot be held back. But infinity is also contradiction. It breaks equations, erases probabilities, mocks predictions. It tells us that every event may occur infinitely many times, and so the very concept of likelihood dissolves. It whispers that the vacuum itself should contain infinite energy, yet observation says otherwise. It suggests that time, if infinite in the past, would already have erased us. Infinity is both the skeleton and the wound of science. It holds up the universe, and yet it cuts through the laws meant to describe it. For human beings, the confrontation with infinity is not merely scientific, it is existential. To look upward is to realize that Earth is not the center, not even a significant place, but a fragile island in an immeasurable ocean. The Milky Way, once imagined as the whole of creation, is itself a grain of dust in a web of galaxies stretching farther than thought can follow. If infinity is real, then the cosmos is not only vast, it is boundless, and our place within it is vanishingly small. Yet this smallness is not only despair, it is also wonder. For in an infinite universe, the fact that anything exists at all becomes miraculous. Amid the endlessness of space and time, a planet forms, a biosphere blooms, consciousness awakens. The rarity of such emergence becomes profound precisely because infinity makes it improbable. Against the backdrop of the infinite, the finite becomes sacred. Infinity also reshapes time. In a universe with a beginning, time itself is finite in age, but its future stretches into uncertainty. Perhaps an endless expansion, thinning galaxies into silence. Perhaps a collapse, returning all to singularity. Perhaps a cycle, birthing new universes in eternal return. Infinity does not settle the question. It deepens it. It transforms the arrow of time into an ocean of possibilities, where endings and beginnings may both dissolve. For philosophers, Infinity has always carried paradox. The spear of Archytas, hurled at the supposed edge of the heavens. Zeno's paradoxes, slicing motion into infinite steps. Cantor's infinities, layered upon infinities. Each reveals that infinity cannot be captured by thought alone. It resists containment, yet demands consideration. In this, infinity resembles the cosmos itself. Impossible to grasp as a whole, yet undeniable in its presence. What does infinity mean for humanity? It means humility. To know that no telescope, no equation, no instrument will ever grasp the totality of existence is to accept the limits of knowledge. We see only within our horizon. Beyond it, infinity stretches, unseen. This recognition humbles ambition. It reminds us that science, though powerful, is a candle burning in a cavern without walls. It means awe. To live within infinity is to dwell in mystery without end. Every discovery, the galaxies of Hubble, the microwaves of Planck, the particles of CERN, is not a conclusion, but an opening. Each advance widens the horizon, reveals greater depths. Infinity ensures that wonder never expires. It means fragility. If the cosmos is infinite, then humanity is not necessary. Life here is not the center of the story, not its purpose. We are a local event, a fleeting phenomenon in a reality without limits. But precisely in that fragility lies value. Meaning is not granted by scale, but by presence. Against infinity, our finitude gives us urgency, depth, and poignancy. Infinity also raises the most intimate of questions. If everything happens somewhere, what becomes of individuality? If there are infinite versions of Earth, of history, of ourselves, does identity dissolve? Or is identity found precisely in the uniqueness of this moment, this strand of time, this singular experience? Perhaps infinity does not rob meaning, but frames it. For even if infinite possibilities exist, only one is lived here, now. Infinity expands reality, but consciousness narrows it into something irreplaceable. In the end, infinity does not yield answers. It resists finality. Every attempt to contain it breaks upon paradox. Every effort to measure it is bounded by horizons. Every equation that summons it collapses under its weight. And yet, infinity remains, as both presence and absence. Perhaps this is its greatest lesson. Infinity reminds us that the universe is not an object to be solved, but a mystery to be encountered. It is not a puzzle with a final piece, but a story without an ending. To live in infinity is to live in tension, between knowledge and ignorance, between smallness and wonder, between finitude and endlessness. The night sky, silent and immense, embodies this paradox. To gaze upward is to encounter infinity, not as theory, but as experience. The stars stretch farther than sight, farther than thought, farther than imagination. They whisper of distances without limit, of time without end. And yet, their light arrives here, to a single planet, to a single mind, to a moment that is finite and fragile. Infinity is not elsewhere. It is here, surrounding us, framing our existence. And so, where does infinity end? Perhaps it does not. Perhaps the question itself is flawed, born of a human need for edges where none exist. Infinity may be the word we give to the universe when it exceeds our capacity to define. A reminder that reality is larger than thought, larger than language, larger than the sum of all equations. In the stillness of the cosmos, infinity is both silence and song. It is the horizon that cannot be crossed, and the horizon that keeps us moving. It is the contradiction at the heart of physics, and the poetry at the heart of being. It is the reminder that knowledge is never complete, that wonder is never exhausted, that the universe is not only vast, it is without measure. Infinity does not end. It unfolds, and in its unfolding, it carries galaxies, stars, and worlds. It carries time, memory, and possibility. It carries us fragile, finite, yet conscious, witnesses to a mystery that will never be finished.